Good morning guys, and welcome to today's worked exam answer video. Today I'm having a look at a time of flight mass spectrometry question, and I really like this question because it goes through a number of things that we need to know about the mass spectrometry process, including ionization by electron impact, including the tricky / dreaded time of flight calculations, and then when we turn over it's also asking us a little bit about the process of detection and how that works and what we can ascertain from that. It then goes on to a relative atomic mass question, which is not the worst I've ever seen, because we're not working out the abundances using algebra, but there is still a ratio that we've got to sort out in there. And then there's a lovely suggest question at the bottom about electrospray ionization. So there's a lot of different components in this question, which I really liked. And I'm going to try to go a little bit quicker because my YouTube videos have been quite long recently. So apologies if you've been watching them and thinking, oh my goodness me, this is way too long. Trying to be concise. So first question, give an equation including state symbols for the formation of strontium plus ions from strontium atoms by electron impact. So we need to understand that for electron impact we fire high energy electrons at the sample, and those high energy electrons knock off an electron from the atoms. So strontium as an atom, and it says including state symbols. Now we need to know that ionization occurs when the atoms are in the gas phase, and those atoms, once they have that electron knocked off, will become strontium singly positive ions, which will also be in the gas phase, plus an electron. Now another way we can do this is we can put the electron from the electron impact on the left side of our equation, and then have a total of 2 electrons on the right, the one that's been lost and the one that was fired at the sample originally. I would prefer to see it this way, but I have seen both allowed, because if you have an electron on the left and 2 on the right, in my opinion, we should always simplify that. So that's my equation. If they don't tell you that you need state symbols, you would still be expect them to put them in here. So make sure you do. Okay. Next question is the tricky time of flight, and this one's not the nicest because we're trying overall to deduce the mass number of this particular strontium ion. So that's the goal. What information have we been given? Well, we're told it's ionized using electron impact. We're told that the ions are accelerated so that they have that kinetic energy. We're told that this particular ion takes that amount of time to travel down the flight tube, and that the flight tube is 95 centimeters long. We're always given this equation, the kinetic energy one, even though there's 3 we're going to need. And then we are helpfully told that mass should be in kilograms and that speed needs to be in meters per second. And that's useful because we're going to be working backwards to get the mass, because we have to if we're trying to get the mass number. So the mass will come out in kilograms and we'll have to change it to grams. Likewise, if speed is meters per second and the flight tube information we've been given is in centimeters, we're going to need to convert that as well. So first equation that we're going to need if we're working backwards to get mass is the equation for velocity, because if we're trying to get mass we can't have another unknown in this equation, and velocity is equal to, or speed is equal to, distance over time. So we've been given the distance, as I said, and we've got the time it takes for that ion to travel down the flight tube. So we're going to have 0.95 meters for our distance, and then the time on the bottom is going to be 9.47 times 10 to the minus 4 seconds. And that gives me a velocity of 1003.2. So now we've got the velocity, we've got the kinetic energy. So the next thing we can do is rearrange this equation. So we want to get the mass because we're trying to get the mass number. So the first thing that I would do is move the half over to the left hand side and have 2 kinetic energy, which would then be equal to mass times velocity squared. If we therefore want mass, we're going to have the 2 kinetic energy being divided by the velocity squared. So 2 lots of 7.02 times 10 to the minus 20 divided by the velocity that we just worked out squared. So let me just pop that down. I think I'm going to go off the page. Whoops. Please make sure you don't do that in your exam, because that bit, they can't guarantee that that will scan properly. So always just cross it out and do it underneath. Velocity squared, so that's then the 1003.2 squared. And that gives me a mass that's going to come out in kilograms of 1.395 times 10 to the minus 25 kilograms. And that's why having that there is really useful, because this is the exception to all calculations. Everywhere else mass is in grams, here it's in kilograms. But because we're therefore trying to get the mass number, and in every other calculation it's in grams, I'm going to now need to put this into grams, and I'm going to do that by timesing by 1,000, which is going to give me 1.395 times 10 to the minus 22 grams. And I'll pop there that I've times that by 1,000. Okay, so now I have the mass, and now we're going to need our moles, mass and MR equation. So we've got mass on the top, we've got moles, and we've got MR. Now it's not going to be MR here, it's going to be sort of AR, but again it's not going to be AR because we're dealing with a specific isotope of the strontium and we want to know the mass number. So that's going to be mass number, and we don't have information about moles, but what we do know is that moles can also be worked out by doing the number of particles that we have in question divided by Avogadro's constant, which is given to us here as 6.022 times 10 to the 23. So I might not know the moles, but I know the number of particles. It's always going to be 1 because we're looking at an ion. One singular ion takes that amount of time. So the number of particles will be 1. We've got Avogadro's constant and we've got the mass. So I'm going to do, to get the mass number, 1.395 times 10 to the minus 22 for my mass. And then I'm going to divide that by the moles, which is 1 divided by 6.022 times 10 to the 23. And that will give me the mass number. Now, because it is a mass number, it needs to be a whole number because the mass number represents the total number of protons and neutrons, and you can't therefore have sort of any decimal part of a proton or a neutron. So that comes out at 84.0, so it needs to be 84 with it being a mass number, so to the nearest whole integer. So there we go. And it's this last part that usually catches people out. So we've been asked to work out the mass number. We know how to get MR, or the mass number in this case, mass divided by moles. We need to remember that we can work out moles this way, and we need to know that the number of particles is always going to be 1 because we're dealing with an ion, a singular ion. Those questions can catch people out, so if I've gone through that too quickly or you have a similar question that you want me to do, as always, please send me all questions either as a comment, or you can email me, Miss G Tutoring and Resources at outlook.com. Okay, turning over. We've now got to explain a little bit about the process of detection. So we have to explain how the ions are detected, and we have to state how the relative abundance of the ions is determined. Now, in terms of the ions and how they're detected, when the ions hit the detector, they gain an electron back so that they become atoms, and that's one of the key reasons why all of the samples need to be ionized before they then are put through sort of the flight tube, so that we know when the ions get to the other side, because they can gain that electron and atoms wouldn't do that. So the ions are detected, think about how to word this, the ions hit the detector and gain an electron to become atoms. And then if every ion that hits the detector gains an electron, we can then measure how many electrons are flowing to the detector as a current, because a current is a flow of electrons, and the size of the current that is generated is therefore proportional to the abundance of the ions. So let's say I only have one ion hitting the detector, then only one electron is going to come to the detector to be gained by that singular one ion. If I had 100 ions coming and hitting the detector, I'd have a flow of 100 electrons. So we can see how the number of ions hitting the detector is proportional to the number of electrons flowing, i.e. the size of the current. So I'm going to say here that the size of the current generated is proportional to the number of ions that hit the detector. And they often ask about how detection works. They also fairly often ask about one of the ionization techniques, so either electron impact or electrospray ionization. So being able to describe those is also really important. The other thing, and I know that this hasn't been asked here, but in terms of reasons why we accelerate the ions before they enter the flight tube, we do that so that all of the ions have the same kinetic energy. Now, if we go back to the equation very quickly for kinetic energy, it's equivalent to a half mass times velocity squared. And if the kinetic energy of all the ions is the same, the heavier they are, the slower they're going to be. Their velocity will lower as their mass increases, and makes sense, and that's how, you know, we can measure those, because we're keeping the kinetic energy the same. We can therefore compare the mass and velocity of all the different isotopes for a particular element. So it's really important that all the ions have the same kinetic energy. And in terms of how we get them to have the same kinetic energy, we accelerate them using a negatively charged plate, and that is the other reason why we need to have ions. One is so we can detect them, so they can gain an electron. The second is so that we can accelerate them, and we use a negatively charged plate. Positive ions are going to be attracted to it, and then they all enter the flight tube with that same kinetic energy. Okay, next question, like I said, is about relative atomic mass. So we know that a sample of strontium contains 3 isotopes, and we're told it's 86, 87 and 88. We're then told the percentage of the 88 isotope, and then the other isotopes are in a 1:2 ratio, where the 86 is the 1 and the 87 is the 2 in that ratio. So the first thing that we're asked to do, which we'll get a mark for, is calculate the percentage abundance of the 87 strontium in this sample, and then use that to help us to deduce the relative atomic mass, making sure we give our answer to 1 decimal place, which should always be the case for AR values, again, whether they tell you or not. So we know the percentage for the 88 isotope. We know that percentages add up to 100. So if we work out what percentage is left, I get that to be 18. So that means that the 86 and the 87 isotopes total between them 18%. Now, if that's in a ratio of 1 to 2, we need to find out what one part would be so that we can then find out what the other two parts are going to be. So in total, we've got 3 parts. So 18 divided by 3 is 6. So the 86 strontium isotopes, there's a 6% abundance for those, and the 87 strontium has a 12% abundance, and 6 and 12 make my 18, and that's then in a 1 to 2 ratio. So whenever we're dealing with ratios like this, we want to divide by all the parts and then multiply up accordingly. So 1 part 6, 2 parts 12. So that's the first thing that we can pop down, the abundance of the 87 strontium isotope. And now we've got the abundances of all 3. We've got the mass numbers for all 3. We know the percentages, so we're going to have 100 on the bottom, and then this becomes just like those GCSE calculations that we used to do. So mass number times abundance, add mass number times abundance, add mass number times abundance, and then because they are percentages, divide through by 100, and that will give us our AR value, which I got to be 87.76, which to 1 decimal place is 87.8. And I'm not surprised to get an answer of that. The relative atomic mass will have to lay somewhere between the mass number of the lightest isotope and the mass number of the heaviest isotope, which is the 88. So we're looking to get an answer between 86 and 88, and if you don't, you've definitely done something wrong. Here, the reason why I was expecting it to be quite close to 88 is because that is by far and away the most abundant isotope of the 3. So these are only going to have a small say in terms of bringing that average down a little bit, and that's why we do a weighted mean mass when we're dealing with isotopes, because we need to take into account the fact that they're not all equally abundant as each other, and if they were, it would be a very different story. But when the isotopes are not equally abundant, which is the majority of the time, the one that is the most abundant is going to have the biggest effect on that relative atomic mass value. Okay, final question. We're told that electrospray ionization is used instead of electron impact for the ionization of a protein in a mass spectrometry experiment, and we have to suggest why. Now, suggest questions are not things that you will have explicitly been told necessarily, unless your teacher has kind of gone through sort of some additional context with you. So with a suggest question, you're expected to kind of use the knowledge that you have to be able to come to some sort of logical, sensible decision answer. Now, I actually did my chemistry dissertation on the mass spectrometry of proteins. I actually did Fourier transform, time of flight, mass spectrometry, and looked at proteins, and the reason why we had to use electrospray ionization is because it's a much softer technique. So when we fire electrons at the sample, there is a chance that the electrons will not only knock off an electron from the atom or the molecule, but it may also cause fragmentation. Now, fragmentation isn't technically on the spec anymore, but it just means that a big molecule might break down into smaller parts, and those smaller parts will then move through the mass spectrometer. Now, that's not helpful when we're dealing with compounds, because we need the whole compound to stay together so that when it gets to the detector, we can figure out its MR from its molecular peak on the spectrum. And so if we get a lot of fragmentation, we might not manage to get any of the whole compound, the whole molecule, moving through the mass spectrometer. So by using electrospray ionization, which is a lot softer technique, we get a lot less fragmentation, and therefore we can work out the MR of these larger molecules a lot more easily. So a protein is a very, very big molecule, and the MR of that's going to be quite big, because it's made up of a large number of amino acids joined together, and that's why we choose to use electrospray ionization. So it's a softer technique. and is thus used for larger molecules. It's not just proteins. Larger molecules generally we'd want to be using electrospray ionisation. The smaller ones, where there's less chance of fragmentation, we tend to use electron impact. So it's a softer technique and is thus used for larger molecules because it results in less fragmentation. Now, I would always mention fragmentation, even though it's not technically on the spec anymore, and I know when I used to teach in a school that I definitely mentioned that, and when I've tutored it with certain students, I have again made that really clear, because I feel like it's an additional piece of context which is helpful. If you haven't heard of that before, don't worry. Like I say, it's not on the spec, and a suggest question is designed to see kind of what you can think about, and kind of knowing a protein is a larger molecule, knowing that electron impact is quite a harsh technique, and then thinking about, in order to figure anything out about the protein, we need the whole protein to stay together. So please don't worry if you haven't heard that before. Suggest questions are the hardest questions that you will get, because you cannot apply knowledge that you definitely have, in the sense of, you can't just go, oh yeah, I remember being told that, and write it down. You have to draw upon different bits of knowledge and come to that calculated conclusion. But anyway, that's today's question. As always, any queries, please get in touch, leave a comment on the video, or send me an email, as I said earlier. Thank you so much for watching, guys. Have a lovely day.